Well, hello everyone. Welcome back to Adrian's Digital Basement. On today's video, we're going to be taking a look at this rather large computer. This is a Plexus P20, which is a computer that, well, I don't really know much about it. And in fact, the only documentation that exists about this computer on the internet is simply these two pages. That is it. Since I was given this computer, I haven't attempted to turn it on. I haven't even opened it up or looked inside. So in this video, I think we're just going to be exploring what's inside of this machine. And if there's a hard drive, which I think there might be on the front here, looks like there is, then maybe I'll pull that out and we'll try to image it. And that's because there's really no software available for this thing either. And if we have any hopes of getting this thing to do anything, we're going to need to recover the data off that hard drive. So without further ado, let's get right to it. Before we take a tour of the outside of the machine and open it up and take a look inside, let's review that little pamphlet that I found that seems to be the only documentation about this computer, so we at least know what we're talking about when we look inside. So thank you BitSavers for having some documentation online so we at least know a little bit about this thing. It says here Plexus P15/P20 Brochure 1985, and the model sticker on the back of this computer says Plexus P/20. So this computer appears to be a multi-processor architecture, high-performance 6810 multi-user Unix-based system with a SCSI disk interface up to 132 or 152 megabytes of storage, floppy drive, streaming tape. It does have a tape drive in it as well. There are two flavors of this computer, and as I mentioned, this is the P20, so the higher model. It's designed for the popular Unix operating system. The P15 supports 8 users, and the P20 adds the addition of an intelligent communication processor, the ICP, which extends the configurability to 16 users. It seems that both of these computers support 2 Motorola 6810 microprocessors, which of course are 32-bit processors. Both of these run Unix 5 Release 2. This is Plexus's implementation, and that's why if the hard drive is unrecoverable or unreadable, that's pretty much going to be the end of this video unless someone can dig up some additional software for this thing. Designed for office use, it's quiet. It's got this giant fan on the back. I guess compared to like mini computers and things like that at the time, maybe for a multi-user system this was relatively quiet, but it's such a huge computer. It'd have to be tucked away into like a closet somewhere, otherwise people will probably complain about the noise. So when it comes to the fact that this thing is a multi-processor system, it says that it links a powerful 1632-bit job processor with a second I/O processor of equal power to remove I/O processing overhead from the job processor. So it's not multi-processor as in two primary processes can run concurrently. It seems that one of the processors is actually handling all of the user tasks and the second 6810 is handling all the I/O. That's still kind of cool because it takes off all the I/O overhead from the main processor, so like disk activity and say tape I/O can really happen in the background without affecting performance of the main processor. Now in the photograph of these two computers, the one thing I'm a little worried about is I don't have the key for this system. It does have a keyhole on the front there, and I suppose worst case we'll have to just drill out the lock. If we open the computer and we find that it's just some pins that go to a little board, we can just jumper over them. Here's a little block diagram of the system, so DRAM and memory map. And then we have the two processors there, the job processor, which has its own bus, along with the I/O processor with its own I/O bus. It looks like from this diagram, they both share the same DRAM, which is kind of cool. That means that the I/O processor can save stuff to disk out of the main DRAM while the job processor is accessing other parts. There must be something that arbitrates the access of the two CPUs to the DRAM though, and I'm assuming that's maybe this memory map here with these arrows. It looks like the 6810 has some static RAM as well on its own bus. Probably if it needs to copy some data out of the regular DRAM, puts it in static RAM, and then it can work on saving it to disk or accessing the tape drive, things like that. Now this is obviously that extra capability the P20 has. It has a multi-bus interface, and I think Intel came up with multi-bus. It was used on a bunch of different systems. It's kind of like the S100 bus in that it was somewhat adopted by other companies. Obviously there's nothing Intel based in this machine being 6810s. And we have some kind of additional multi-bus backplane inside that case, I guess. So we'll have to see what kind of cards are installed in there. And looks like you can have additional stuff. This is the one that it comes with. It mentioned that on that first page, but then it has, well, other multi-bus controllers, which you can add. On the third page, talks about the fact that there are some self-diagnostics in here. Let's hope that they work and that they're easy to follow because, well, there's just no documentation, so we are on our own. The CPUs run at 12.5 megahertz, looks like 64K of ROM, and we have that 16K of static RAM for the I/O processor. And it looks like we have up to 8 megabytes of address space available for DRAM. The 6810 is basically just like the 68000 with some slight optimizations. It can support up to 16 megabytes of RAM or RAM, ROM, and other types of devices on the bus. And it looks like they chose 8 megabytes. The Macintosh, of course, is famous for only supporting 4 megabytes of RAM, but then something like the Amiga does support 8 megabytes on the 68000 machine. So kind of similar in that way. There are 8 serial ports on the machine. We'll see that in a second when we look at the back. They're just 9 pins, except for I think a couple of them might be 25 pin. It's handy that we don't need some kind of breakout cable that I don't have, so that makes hooking up terminals very easy. Looks like the additional card in the P20 is some 16-bit processor that's on that multi-bus interface. We'll have to take a look at that. 32K of RAM there, 16K of ROM, and it looks like some additional serial interfaces are available there. The job processor, which is the one that the operating system, or at least like the user processes run on, is also running at 12.5 megahertz, has 8 megabytes of RAM. It does have a battery backed up clock calendar. That's pretty worrisome. I just saw that. I actually looked at this before, but I didn't notice that it has a clock. Hopefully that didn't leak and damage anything. And it says here that the memory capabilities of the system is only 2 megabytes. So even though it has 8 megs of address space available for RAM, 2 megabytes is all you get. Standard 256 kilobit DRAM though, and I saw up above it does use parity, so there'll be 9 chips of those. Luckily that's really easy. I have plenty of those chips, so if there's any RAM problems, we should hopefully be able to solve them. And on the final page, looks like the 5¼ inch floppy drive, which is in there, is a 96 track per inch drive, which is just typical like high density format. It's probably running a double density though. Oh yes, it is 640 kilobytes here. So on a PC, that would be 720 kilobytes for an 80 track disc, double sided. So pretty standard. So if the floppy drive doesn't work, that's no problem. I can put a spare in there pretty easily. And the tape drive is a QIC11, 45 megabytes per tape. That's a 9-track tape drive. I don't have any of those tapes. I think they pretty much self-destruct with the rubber and the belts and stuff inside. And what's worrisome is it's quite possible the original operating system for this machine was distributed on tape. And you would have a boot floppy of some kind, and then it would use a tape to restore the OS back onto a hard drive. Say if you had a hard drive crash, you had to start it from scratch. That means it's probably unlikely that anyone ever archived those tapes. So that's probably why there's no software floating around for this thing. So let's hope that the hard drive in here is working so we can try to recover it and hopefully gain access to the Unix system that's on here. And down at the bottom, the very last thing, it says Plexus Computer Incorporated, 3833 North 1st Street from San Jose, California, and the date there, 1984, 1985, Plexus Computer Inc. I couldn't really find anything else about this company out there, so I'm gonna have to rely on you, my viewers, to do your usual internet sleuthing and maybe turn up some more stuff about this machine. Okay, over to the actual hardware. So on the top of the P20, we have a full height 5¼ inch floppy drive, although inside I've seen these before, it's just a half height mechanism. Looks like there's a blank here, maybe for the hard drive, a half height hard drive of some kind, and then there's the tape drive mechanism right there. It did say in the documentation that it was SCSI. Moving down, we have the Plexus logo embossed into the plastic. Pretty nice design element. And on the upper right corner of the front panel, we have the status display, P20, and we have 0 through 7, which is obviously for the active users, I guess. And it does say system power, and there's that key cylinder, which I don't have the key for. Looks like the glue is coming off a little bit here, if it does move. We have LEDs in all the positions except for 3 and 2, which maybe those fell inside. We'll have to see when we get this apart. I had to move the camera pretty far back just to get in the sheer size of this thing. It is very heavy and very large, big swath of beige there. It's actually a metal computer as well, so moving this thing around is it's not easy. This large plastic piece at the bottom here, which contains the feet, also is an air intake of sorts because, well, there seems to be a big gap in there, and I'm assuming air enters the bottom here and then goes into the case. On the back of the machine, it's pretty large with this huge fan at the top. We have serial ports starting with 0. The board does seem to be moving around a little bit. 0 through 5, a little bit of rust on this screw right here, and then we have an access panel of some kind, which maybe that's for that expansion interface that uses those multi-bus cards. And then we have 2 25-pin serial ports labeled 6 and 7. Looks like some kind of an expansion interface here, some pin header thing. Maybe this is for a UPS. It did mention that in the documentation that it supported an external UPS. Here's the mains AC input with a fuse and a voltage selector. It's multi-voltage, and there's the model number and serial number for the computer. I am definitely not just going to plug this in and try to turn it on. We're going to open this thing up and take a look inside because I want to get that hard drive out of here and hook that up externally to see if we can image it. So let's see how serviceable this thing is. I have a little screw holder here for loose screws if I take any out. And I'm just going to start here where it says open or close. I'm assuming we turn counterclockwise for loosening it. Okay, these seem to be captive. That turned and then stopped. And now it's just a matter of figuring out, oh, it's sliding forward. Okay, the entire top chassis seems to slide forward with the front panel. So let's turn this around so we can slide this off and reveal the insides. You know what, we're looking at the bottom of the board. Okay, that might be okay. Let's just get this off here. Ooh, it's so big, it is so big. Wow, wow, look at that. It's huge. It's such a big circuit board and there's so many bodge wires on it. That is freaking amazing. So right there we have the clock battery, and luckily it's in one of those epoxy things, kind of like a Dallas clock. That's excellent. So that means it hasn't leaked anywhere on the board. If it had, it would have caused massive damage. Looks like the board is somewhat relatively easy to service. There are these little thumb screws right here that probably allow it to come out somewhat easily. Now I'm noticing right off the bat, there's something funny happening at the front of the case. This board here, which connects there, is like the expansion chassis, probably for the multi-bus stuff. It's just kind of loose. And that comes away. And I don't know if this got banged around like in shipping or something. Pulling that off, there's that expansion board. Now the funny thing is this doesn't look like multi-bus to me. I thought multi-bus has this, plus an extra little pin header, a higher density one, down on the side. Now what was this board here? This thing just simply has a bunch of resistors on it. That's kind of odd. Is this just to burn power? Now, if you look at the main motherboard here, you can see a row of pins. There's obviously some type of an expansion interface or header connected here with something plugged in on the back. And when I look down inside here, I can see that there's an additional board there. And obviously this is the large hard drive that's in here, so I'm gonna need to figure out how to get this out of here so we can try to image it. This, I'm assuming, is the power supply unit for the machine. And hopefully that comes across on the camera, but there, this board right there that's sandwiched on, connected with this connector right there, that's obviously the DRAM board. There's a whole bunch of DRAM there. The expansion backplane, part of the P20, has these levers here, which are kind of cool. Looks like you can twist these to release the tension on this and get the cards more easily in and out. I think it's a kind of a locking mechanism. When you twist them into this one position, it clamps down on the card to prevent them from coming out. And yes, indeed, it says here to open these, you turn them that way, and it opens them, and turning them left, I guess, latches down the card edge connector. So let's give that a test. I'm gonna switch this to the open position. Yeah, look at that. Wow, it opens that whole thing up, and I can place this card into the slot, turn this back to the closed position. Yeah, and I think that's grabbing onto it now. I have to say, I don't think I've ever seen that kind of mechanism before, but kind of cool. With the computer rotated around, we can see what looks like a giant power supply board here. I'm assuming both of these are power supplies. This is probably an additional power supply, now that I think about it, for the multi-bus interface. And this board here, which has a ton of wires there, must be the power supply for the primary part of this computer. Both of these are made by Data Power Incorporated. And this one nicely has actual pinouts for everything. 5.1 volts, minus 12, plus 12, plus 12, plus 5. Yeah, it looks like pretty standard stuff there. Although this part down here is 300 volts DC output. Not sure what that's for. V-bias, shutdown. Looks like to get this out, you can loosen these screws here, slide this up. These are slotted, and then perhaps that kind of pops out. And this power supply here looks like it comes out in exactly the same way. Now, looking at this hard drive down here, we can see the bottom of it. It's a little bit concerning because it said it was SCSI, but we're looking at what looks like an MFM connector here. So there's probably an interposer board that goes between this and the main motherboard. And the main motherboard has a SCSI interface, but you need that interposer board to convert the two. Now, luckily I have a way to archive MFM drives. So I guess the first thing we need to do is get this thing out of here, which looks like you could just release these screws and probably goes out that way. I gotta find that interposer board though. I want to try to archive it with the interposer in place. And if all else fails, I'll hook this up to the MFM emulator, and then I should be able to dump this as well. Now I'm looking way in the back there, and there's sort of this beige thing there, and that might be the interposer that is converting the MFM drive to SCSI. And looking at the motherboard, we have the SCSI interface here, and that definitely is not MFM. And the 50-pin ribbon cable is visible there, and it kind of goes down. So it looks like the interposer is behind the motherboard, which means I might need to try to take this out of here. When we look at the key lock and the switch that's behind it, this should be no problem at all to bypass. We just have to kind of figure out the pin out of how this all works. And luckily, when it comes to the LEDs for this front panel, they're just sort of pushed out of position. That's why I didn't see them when I was looking through. There we go. Now they're back in position. Now looking at date codes on these ICs, I am seeing 28th week of 1984. There's stuff from 1983 on here and a bunch of stuff from 1982 early on. But the dates kind of go all over the place. But the fact that that says 85 on that chip that is soldered on, that means that this board was almost certainly built in 1985 or after. As you can see here by these wires, there's a serious amount of rework that's been done on this, and they did a nice job though. The wiring is meticulous and really well applied. There's glue holding it down in the right spots. Up here, you can see a bunch of it, just very meticulously applied. This chip here is a little haphazard. It's in a socket. Whoa, the label just fell off. It's a PAL chip. I'm just gonna get a piece of tape and stick that back on. But the bodge wire that's going to that chip, which has several legs that are lifted, it's all a little sketchy. So I'll just put a little tape on there to hold that label back on. So looking closely, we do have signs of corrosion right here around this clock battery. Very unfortunate. There's some green stuff on those resistors there. A few traces don't look so great. It's very minor. It doesn't look, it kind of went down on these chips just a little bit, but everything over here is completely fine. It's just in that one little area. Let's see if we can get this out of here. There's a thumb screw on the motherboard. I think this might slide out potentially, slide forward. Okay, with that out, it's captive. Does this move? There are some push pins here. I wonder if those need to come out. I think those are holding, I think they're holding the RAM card on, so I'm not sure those actually need to come out. I'll unplug these connectors on the top here. Oh, and I just realized there's another one of those thumb screws right here. If that's all it takes is 2 thumb screws to slide this out, that's very nice and serviceable. Now does it slide? It does. It has some notches on the top, so I can lift this up and out. So that's one big logic board. And let's flip this over so we can look at the RAM card on the back. There's the RAM card. Interesting is theoretically you could have more than 2 megabytes, but this obviously is just 2 megs with these 256 kilobit RAM chips here. So 256K, this is 512, 1 meg, and 2 megabytes with that memory. Thank you very much, Plexus, for putting all the RAM in sockets. At least I'll be able to take them out pretty easily for testing purposes or whatnot. On the back here where the battery is, this looks okay. I don't see any corrosion, nothing too bad. There are these large pins here. I assume those are kind of sockets. So I think this battery is actually not something like a Dallas where the chip is inside the epoxy. I think it's literally a battery, and these pins probably supply the charging current to the battery module itself. So that means we can take it out and hopefully the computer will still work without the battery, and then maybe we can just supply it with a little bit of a CR2032 for when we actually power this up. With the motherboard out, we can see that the hard drive is right here, and that's the power supply module, and there's another one right here. And definitely behind this is the interposer that goes from MFM to SCSI. I can see the MFM cables coming in down here, and SCSI comes out on the top. So I popped these 2 covers off the back, and that gives us a little bit more view into that interposer there, but I don't quite see how to get it off. It uses a normal Molex style power connector right there, but something is holding that on. Part of me has me wondering, do I need to take this power supply out? And I have loosened the screws, but it is really heavy, or all these cables in here are really holding that in place. Okay, there was one more thumb screw on the power supply. Seems that the mains IEC input is attached to it, and with that, I was able to lift this up and get it out. Well, I haven't got it out yet, but I was able to lift it out. Let's see what we can do here. This thing is pretty cool how it's designed, but it's also a little unwieldy in some ways. With this tilted out, you can see the interposer. Looks like this is held on maybe with a little tab right here. Let's pull on this. I'm pretty sure this is some kind of a push pin situation. Oh, that is really stuck though. And as far as that little push pin goes in there we go. I used a tool to pull that out. Put the power supply back in there. Just needs to kind of sit in there. Looks like the interposer is made by Omti Incorporated. Omti IE9, but I can see the brand name down there on the bottom edge. It's actually a floppy drive controller and a hard drive controller. There's a regular NEC FTC 765, and then those are the data cables for the MFM hard drive. So the 6810 system, as it's addressing the floppy drive, is doing it through this SCSI interface. So next, I gotta get this MFM hard drive out, slide these off, get the screws out of here. We'll just loosen them up first. I'll take the top two out last. All right, the hard drive, I'm just gonna hold on to it while I get these top screws out. The case design actually has a little retention mechanism in there, so the hard drive doesn't just fall out when you take the screws out. That's kind of nice. There are some really thoughtful touches put into this case. This bar right here is what I was talking about, holds the hard drive in. So I gotta unplug the Molex power connector for the hard drive. Just slide it out the front. There we go. Full height MFM hard drive. A big beast. Made by Fujitsu Limited, part number B03B-4805-B003A. That's quite the long model number. Date is 1985-9, so 9th week, I suppose. I have the motherboard on the bench. The reason why I have this paper here is because the stickers have fallen off the EPROMs there. So before I take those out, I'm just gonna cover that up. So when I was first looking at the machine, I noticed that this panel seemed a bit loose, and it turned out that one of the tabs was actually snapped off. So last night before I went to bed, I actually got out a little JB weld and I epoxied that back together. So that way, well, when we put it back together, this thing won't be loose anymore. I also went ahead and disassembled the front switch here with that key lock cylinder, which I think I am gonna have to drill out. Now I could just jumper these wires here to get the system to turn on, but the way this works is there's two micro switches right here that get pushed on when you turn the cylinder. On the back side here, when you turn the key, it actually pushes these little plastic pieces here which line up with those micro switches. So I think the easiest thing to do is just mount this in a vise and I'll drill out those pins. I don't have any skills to pick this lock, so that way I could just turn this with a screwdriver or any other key. What I want to do in the rest of this video is I want to dump the EPROMs that are on this board. There are 4 here, and I want to dump the one that's on the SCSI interface board as well. And then I want to take this battery off here. In fact, let's just do that right now, because I feel that we should probably start cleaning up the corrosion that's going to undoubtedly be underneath this thing. Oh yeah. It's probably a NiCad battery inside there, judging by the green crusty corrosion. And on here, yep, same thing. A little bit of green crusty there and there. So let me clean this up. Let me get rid of this zip tie first, and then I'm gonna clean this up. So I just first sprayed this with a little bit of IPA, and luckily the corrosion is very minimal. It's not super bad. Obviously these 2 terminals have some corrosion on them. Well, all 4 of them have some corrosion, but I don't see any broken traces, at least not initially. I'm gonna hit this with a little bit of vinegar just to see if this reacts at all. See if there's a strong base there with that corrosion. That's what the corrosion is from these types of batteries. It's this very strong base. In case you are curious what this is, it's a Data Sentry from GE, model number DS3SD. Nickel cadmium battery. Yeah, bad. Luckily it was mostly sealed up. Okay, so I have some vinegar inside here. It looks black because there's some spray paint on here. So I'll just put this on a cotton bud here. And we'll wet the area, and I'm not going to wash this whole motherboard. I just want to wash this one little area, and I can put IPA on it afterwards just to wash this vinegar off. Luckily, I'm not seeing any kind of strong reaction. There's no bubbling or anything. So I think the IPA probably washed off the majority of what had leaked onto the board. Now, while I wait for this vinegar to soak in a little bit, I can see here an MC1468 18P. That is the CMOS battery. It's a very standard chip used on all sorts of PCs and whatnot. In fact, you can just replace this entire thing with a Dallas type clock or one of the modern replicas, and then you don't need to worry about even installing a battery because, of course, the modern replica will have its own battery. I did a very similar swap on my PC 5170. It's an IBM 286 board, and I also did it on the BBC Master 128. And yeah, I swapped this chip out with the modern replacements from Necroware, and that way I wouldn't have to worry about any batteries in the future. Okay, I think I've cleaned this up about as good as I can. I let that vinegar really soak in, then I washed it all off with IPA. A bunch of the green corrosion, at least from those 2 pins there, did come off on a paper towel, but the rest of this looks in pretty good shape. I don't see any corroded traces, although it's possible. There's some that look a little bit dodgy, but should be easy enough to fix. As far as the lock goes, I was successful, but it was very destructive. The entire thing kind of blew apart. And I do have it with some glue on there right now. That's why it's clamped. Let's see if this still turns. It does. I'm kind of concerned that the glue is going to lock the cylinder, but now we can turn this. And if you look around the cylinder, see there's a little pink looking pin there, and if I turn this, then a white pin is going to appear. And those are what push on the micro switches to turn it off and on. So now a key is just a screwdriver or any other key that fits in there. So now I'm just going to spend a little bit of time removing these EPROMs one by one. I'll put them back in the board so I don't mix them up. And I'll also pull the one out of the SCSI adapter here, and I'll upload those along with some photographs of this to my GitHub. There'll be a link in the description. On the motherboard, there were 4 total ROMs. They were 27 128s. And since it's a 16-bit system, there are high and low byte ROMs, and I merged those together and we ended up with 2 files, U19 and U17. Let's start with the U17 merged file. I have a feeling this one is for the program processor or whatever the main one is that user processes run on. If we scroll through this stuff here, we will end up where there are a whole bunch of strings. Unknown device, bad offset, unit specifications, unable to wake up disk controller, bad disk read, invalid disk init block, unable to wake up tape controller, bad tape init, bad tape read, bad tape seek. What's fascinating here is that it looks like it's actually able to read the tape drive into BIOS routines or whatever, like the ROM routines here. So it's not just an OS thing. I shared some of the stuff I've been finding with this computer with my patrons, and one of them mentioned that there was a Sun Microsystem computer that was from the 80s, around the same time as this machine, and it also used an internal SCSI tape drive and a hard drive, and that user told me that it actually booted the system from the tape drive, and if you needed to recover the system, you'd actually boot the main OS off the tape, and then I think it would reinitialize the hard drive or whatnot. And I'm wondering if this Plexus thing actually works the same way. Continuing on, we have unix.pt, sys5.pt, format.pt, make file system, restore, file system check, file backup. They all seem to be pointers that maybe point to these particular utilities. But here we are with a boot string, Plexus primary boot, revision 1.2. Looks like disk, boot disk not formatted, boot unknown controller, boot phony SCSI address. That's a phony address. Looks like there's some kind of routines in here to actually format a floppy disk. Yeah, it looks like it. Bunch of drive errors and things like that. Records not found. Write protected. Correctable data field error. Just all sorts of system status related stuff. And it looks like we have exited where the strings are. So we'll just kind of zoom through this. I think that was generally it. Oh no, here's a little bit more at the very bottom here. We have a bus error, address error, bad trap. This is almost like some kind of diagnostics thing. Some more SCSI stuff, bad controllers, SCSI registers, TTY command, halted. That's the last message. And we get 0, 1 through F for some hexadecimal conversion routines. And that's it. That's all that's in this ROM file. Moving on to the U19 merged file, this one starts out right here with RD32, and then there's a date, June 4th, 1985. There is a little bit of text in here somewhere. There's some diagnostic routines that I found looking at this earlier. Here it is. Self-test, revision 3.3, self-test complete, self-test failure. And it looks like maybe these are some of the messages here, proms, statics, SIO, stuff like that. So maybe the IO controller outputs this immediately over the serial port when you first power on the machine, and then it hands it off to the other ROM for actually booting the system. I wonder if this is a kind of RAM test here. Address something something, received something, expected something. So this might actually be telling us if there's a bad bit, for instance, with what's written to memory and then read back. That could be helpful. Interrupt received, it expected something else, received, expected, timeout, monitor. And the last message in here says failed, no boards. I did also dump the ROM that was on the Omti SCSI controller. I don't think there were any strings in here. I took a quick scan. I know I'm not using a strings command, which would quickly identify any strings. Potentially inside the SCSI controller, the only thing we might have is like the brand name, showing like the SCSI response from when you query this unit. Because of course, SCSI does show a brand or a drive or whatever when you query. And I didn't see anything in there. But at the very bottom here, it does say right here, 5200 VE. And my assumption is this is a date, August 28th, 1985, although there's an extra 9 there, so not totally sure. And that dovetails into the interposer that's in this thing that converts the ST506 MFM style hard drives into SCSI. And I was able to find the actual manual for the interposer, and it's the Omti 5000 series SCSI Intelligent Data Controller. And remember, that string in the ROM file said it was the 5200. So let's look in here and see if that's an actual model number. Oh, yep, there it is. Omti 5200, Winchester, and floppy drive, which is pretty much what I already figured out. In this circumstance, a Winchester is the actual hard drive itself and floppy drive interface. And looks like they had versions for tape and floppy. Now, what I'm curious about with this interface is the number of heads and cylinders fixed inside the controller, like in that ROM that's on there? Or is this something that it figures out on its own? Or is it something that's configurable from the host system, like via a SCSI command? It says here it supports drives up to 65,000 cylinders and 16 heads. So that's far more than hard drives at the time this thing was released, which was 1985. Now, this Omti interposer uses a Zilog Z8 microcontroller, which is kind of like a Z80 processor. I think the instruction set's pretty similar. In case anyone's going to try to disassemble the ROM that's on the Omti board, then make sure you set the architecture to Zilog Z8. The reason why I'm concerned about this heads and cylinder thing with the interposer is the battery that was on the computer, it obviously is bad. So we've lost the equivalent of the CMOS settings. And if there was something set in there that then went and configured the heads and cylinders on this SCSI interposer for the drive to work, then potentially the system is just not going to boot, even if the drive is working, because we've lost those settings. And so far, I haven't seen anything to say that this thing auto-configures itself based on the heads and cylinders, because that is theoretically possible. It could do a little process to do that. So I'm looking through all the commands here. Looks like tape commands. Look, assign disk parameters. And there it says for the Winchester or the floppy drive. So that might there be the command to actually configure that interposer for the hard drive specifically. And I'm assuming because it says in the paper that you could have 2 hard drives, for instance, in this thing, that it supports larger hard drives than the one that was actually in there. I looked up the heads and cylinders for that drive that we took out of that thing, and the capacity is only 68 megabytes formatted. But remember, it says right here that the maximum capacity that the Plexus computer supports is 152 megabytes, which actually is kind of curious now because it shows formatted capacity as 76. But I think that this drive is 68, but I actually did find the original brochure for it. Here it is. This is that Fujitsu drive. There are a whole bunch of different versions of it in different sizes as well. And I think the one we're dealing with here is this one, M2243AS, where the formatted capacity is 68 megabytes, which actually matches what it says right here on this list. But the unformatted capacity is 86. Okay, so that maybe makes sense because that formatted capacity is probably for MS-DOS, and maybe the way this formats the drive actually results in 76 megabytes. So back to the Omti controller manual, looking for stuff to do with configuring the drive. There is some jumpers on here that let you set the bytes per sector. And here we go, default parameters. Winchester hard drives, upon power on or any reset, the controller defaults to the following parameters. The byte numbers and hex values refer to the parameter list. Step pulse width, number of heads 4, cylinders low and high, 153 cylinders, and number of sectors per track based on jumpers. So, okay, so it's defaulting to a drive with only 153 cylinders and 4 heads. That's going to be maybe like 5 megabytes. And the reason why I say that is 153 times 4. Yeah, a Seagate ST255 is exactly 615 cylinders, 4 heads, and that's 20 megabytes formatted. And this seems to default to some drive that is just a 5 megabyte in size. Maybe it's just a safe value. And continuing on, it just seems to talk about other stuff like disk drives and things like that. Yep, and there we are at the bottom. So there's absolutely nothing about setting the parameters and then saving them. Now, the only thing that might be possible is maybe once you set the parameters, it saves it to some part of the disk, like the very first sector, and then next time you power it up, it should read that sector back and configure the interface. But I'm doing another scan through the manual. It doesn't say anything about the fact that the parameters can be saved. It just seems to say you have to use the assign disk parameter command, and I'm assuming that has to happen every time you power cycle the system. I'll worry about the whole drive type parameter stuff when I actually get to the point of turning on the computer with the drive in there, if we even have a working drive. I think I'm really counting my chickens before the eggs hatch here, because honestly, the drive might be totally dead as it is. MFM hard drives are notoriously unreliable, and if that drive is, well, not working anymore, well, I think there's really no hope for ever getting this computer working beyond at least seeing that diagnostic stuff when we power it up. So to that end, I'm going to stop putting it off, and it is now time to try to actually power up the hard drive from the machine. This is not one of them. This is my hard drive MFM emulator. And the cool thing about this is not only can it emulate hard drives, and that's what these connections are for, but you can plug an MFM hard drive into it, which I have this Seagate ST225 plugged into it, and then you can archive or image the disk onto the BeagleBone. And this has a BeagleBone underneath here, which has built-in memory, and I'm connected via Ethernet over SSH. The idea is you analyze and you recover the drive onto an image, and then you can restart this in emulation mode, and then I would be able to plug the SCSI interposer into these connectors here, and then this would actually emulate the physical hard drive. It wouldn't need that drive anymore. And of course, we then have a working image, which I can copy over Ethernet to, a modern computer, and we can analyze that and see what's on there. Now, the reason why this is hooked up as it is here is that I always forget how to use this thing, so I had to refamiliarize myself with the commands and whatnot that this uses, and I was using this untested Seagate ST225 to actually test the archiving or imaging abilities of this device. So what you see on PuTTY here is me actually trying to image this Seagate drive. Now, one of the things about this drive, and I've never tested this one, is it seems to have a problem on head 3. So as I was reading through, there were all sorts of issues. Now, in the end, it gave me a summary of what happened. It expected to read 41,820 sectors, properly that is, and it actually got 41,216, which meant we had 599 bad data, and I guess 5 with bad headers. So there's a whole bunch of bad sectors on this drive, and they all seem to be coming from head 3. Scrolling back here, you just see there's like tons of errors. Now, a lot of them do recover. Well, sometimes it doesn't. Bad sectors, and it tells us which sectors are bad. But other times it says all sectors are recovered after 1 retry or 3 retries or whatever. So even though there were tons of errors, in the end, well, 600 bad sectors, not great. But on this hard drive, we're able to read the image that was created with this device. So we can look at the partition table here with fdisk, and it looks like we have one FAT16 partition. Now, one of the problems is this is a drive image of the entire thing, including the partition table. So I don't think there's an easy way for me to mount just that one partition that's visible right there that starts at sector 17. But another program that's actually kind of useful is this thing called FATCAT. And this thing allows you to specify an offset. And if we look at the number of sectors that the partition starts at is 17, you do 17 times 512 for the sector size, that gives you 8704. And this allows us to actually list what's on this hard drive. And there it is. Like, I never hooked up this hard drive to a real PC, but we can actually see what's on here. WordPerfect, Lotus, some games, Lotus 123 again. SpinRite was run on this thing at one point. There's Park Command, a screensaver, label, just random typical PC XT stuff that's on here. Now, another thing that's super awesome about this particular emulator is it understands many different formats for MFM hard drives. The thing about MFM hard drives is that the format that's actually on the disk is specific to the type of controller that you're using the drive with. An ST506 style hard drive or MFM hard drives are pretty dumb devices, and that means that the controller writes the bit stream directly onto the disk or reads it back. So unfortunately, that means one controller to another is totally incompatible. Now, it's not to say you couldn't just take an MFM hard drive that was used with a different controller, low level format it, which sets a new base format down, and then you're going to be able to use it just fine. But if you're hoping to recover data off of it, well, then you need to understand what kind of controller made it so that you can make heads or tails of the format on the disk itself and decode that. Now, what's really cool is that this MFM emulator supports an absolute ton of different formats. And these are just some of them here, like Superbrain. Oh, Western Digital 1006. This was the format that IBM created for the IBM PC 5170, the 286. So pretty much all 16-bit MFM controllers that are modeled off of the one that was originally in the 5170, I'm pointing to the one over my shoulder here, they all use this WD1006 format. In fact, this hard drive here, the one that has the bad sectors, when it started analyzing and then dumping all the data off of it, it said it was that particular format. But as you can see, we have a ton of different formats here. Another couple Tandy formats. There's a Motorola format here. Acorn had a format as well, Electronica. But if we scroll through this list here, there it is, Omti 5510. I'm assuming that's the format used on the 5510, the 5520, and the 5530. And we have a 5520 here. So that means that this thing should easily be able to decode the format that's actually on that disk if it works. Now, the best of my understanding is if you're using a format that's not understood by this, it still can image the drive and then emulate it because it just is emulating the bits, right? But when it comes to decoding an image file that you could then use, say, with an emulator, that's where it needs to be able to read the actual format. And it's pretty cool that this SCSI interposer is one of the ones listed here. I think I have delayed things enough. Let's plug this into power and first of all, see if it even works. So I'm just gonna reposition things here a little bit. I'm gonna power off the power supply. Notice there's a red light on there. It's because it has supercapacitors, so that thing is able to stay running even after you turn it off. The very first thing we're gonna do is we are gonna power up the power supply without the data cables connected. We just wanna see if this thing spins. I'm gonna put my microphone right next to it so you can hear exactly the sounds that this thing makes. Okay, so obviously it's spinning properly, but I was expecting more head activity sounds, and it doesn't sound like it's doing anything. I'm gonna power it off. Yeah, I didn't hear any head noises at all. I will connect up the ribbon cables here, and we'll power this back on again. Takes a moment to start spinning. I mean, I'm thinking the heads might be stuck. That's what I'm thinking is happening here. The servo speed control is good. I don't know, that maybe that's why actually. Maybe that's the sound of the heads being loaded, because there was sort of a chick sound, and I don't know. We're going to rely on the tools itself, the MFM read command here, to try to analyze this hard drive. So you don't even have to specify the heads or cylinders or sectors. It figures all that out using the analyze command here. So I'm just going to save this to plexus try1.emu. That creates an emulation file that can be turned into an emulator here, and also an extracted data.img file. So that only works if it can understand that this is the Omti 5100 or whatever. So let's see what happens here. If this can't control the heads on this, we'll know pretty quickly. All right, RPM is a bit high. It should be 3600. Is the light on? The light is on. So this always can take a little bit of time here while it tries to figure things out. But I am a little concerned that it's not going quicker than this. Usually there should be some more feedback. So it did detect that it's an Omti 5510. That's something, and the sector length is 512. But I haven't heard it seek yet, and that is still very concerning to me. Oh, it's seeking. All right, all right. So interleaved, it has 18 sectors per track. You can see there where it says interleaved. And now it's scanning all the tracks. It's looking for the top cylinder. I can look that up. Let's see, what is the top cylinder? Right here, 754 cylinders. Uh-oh. Oh no, bad blocks already. So it found 754 cylinders. There it is. 18 sectors, 11 heads. Whoa, this thing's got massive amounts of heads. So bad block though. Oh, the bad block was set. Okay, that's okay. That means that these blocks were already marked by the interposer board when this drive was formatted. This is different than a read error. This is actually understanding the format of what's on the disk. Oh, we're getting a successful read here. This is excellent. This is absolutely excellent. So it looks like a sector or a track was marked bad and an alternate track was specified, which is what it's doing there. Alternate cylinder assigned to cylinder 734. And this is why it's important that we're using a drive that was made with a controller that this actually supports. Wow, there's a lot of bad blocks set here. I guess this is a large hard drive because it has so many heads. Okay, fingers crossed that this actually works. I'm gonna stop talking and I'm just gonna pay attention now. Okay. What happened here? Found cylinder 0 to 753, expected 149,292 sectors, got 148,680, 0 bad header, 0 bad data. 612 sectors marked bad or spare, 0 sectors corrected with ECC, track read. Okay. I think what just happened is it just worked. We got a good image from this drive. We got a freaking good image. That was nerve-wracking. I was honestly worried that that wouldn't work properly, but it totally did. At one point, when it was reading the drive, it was up near the end of the drive in those 700s, it started getting noisy, like as if the head was moving over a damaged part of the disc. Like there was, yeah, it didn't sound good. But once it moved past those tracks, it went back to normal sounding, like just the noisy sound it has here. But luckily, everything was marked out as bad anyways, and they used those extra cylinders up at the top to, you know, reallocate those sectors, and it just works. Oh, wow, okay. All right, so I think at this point, let's turn this thing off. The head parks itself. That is good because that computer was banged around, I'm sure. We'll turn off unplug the power there, unplug this from the emulator. And we'll turn the power supply back on so the super caps can keep running the emulator. And what I need to do now is SCP the file off of the BeagleBone and copy this onto my bench machine so we can open this up in a hex editor and take a look at the data we see. Oh, you know what? Just for fun, where did that go? Okay, let's see if we can actually fdisk or look at the partition table on this. Okay, so we see two files here. One of them is Plexus try1. Now they're both try1. I thought that there were going to be errors. I have to do this multiple times. I accidentally called it try2. The .img is the decoded image, and the .emu is the actual raw data. It's almost like a flux copy of the drive. So if we're going to emulate this, we would use the .emu file, and then the Omti controller wouldn't be able to tell the difference between the emulated drive and this actual hard drive. But for looking at the data, like if we're going to do an fdisk here, we need to actually load the img file. Okay, I'm not going to write this. Okay, no, Linux doesn't know how to understand this. I mean, it's not surprising, right? This is a Unix partition from an operating system that was way before Linux was even dreamed up. So, okay, I just thought we would take a look at that. Actually, let's see it. String seems to be installed on here, so we can do strings on the image here. All right, /Unix. Oh boy, seashells on here, profile. I don't even know like who had this computer or what's on here. Measurable, U-disk. Oh boy, oh boy. Ah, look, here's some more stuff. Message key, SH key. I mean, there's no network interface on this thing, so it's not gonna be telnet or any kind of servers or anything. This thing is completely standalone. Look, there's commands here, alias commands. I mean, I know this is completely run-of-the-mill, but it's pretty cool to see this. Okay, so there's the time zone, PST 8, so here it's Portland, I guess. VT100 terminal, perfect. I got a VT220 that's working, so we can hook this thing up to it. It has mail on here. Who's sending mail? I guess like from one user to another. User/PLX/WBS. We have environment variables for something called qlib, whatever that is. Got some errors and things here. Broken pipe, argument out of domain. There are some files here with .c on it. That'd be pretty cool if there was a C compiler because we could actually port some stuff over to this thing. Yeah, a bunch of C stuff here. String compare, string copy. So this might have the compiler installed on it. Yeah, look at this. Makefile, release, reading internal rules, reading environment. Look at this, System 5, release 2.0, and there's a date there, September 1st, 1983. Looks like we have the contents of a makefile here, so has the C compiler stuff and all the flags and whatnot. You know, one of the things that has me worried here is that we don't know the password. So hopefully this uses like a password file with some like MD5 thing we can just reverse, and maybe we can find it in the disk here and reverse the password out for the root account. Check it out right there, etc password. So yep, it does use a password file. We'll just have to figure out how to find it. Looks like we have password and O password, whatever that is. Password user, yep, that's for changing the password. So old password, sorry, so many weeks since your last change. Let's grep for root with a colon, because I think that's the format of the password file. All right, so are these the passwords, the MD5 passwords right here? There's a bunch of them. Maybe there's like a bunch of backup copies of this file. All right, I'm gonna have to ask someone to help me reverse these passwords. So when we get the system booted, if it boots, then at least we'll know how to log in as root. All right, well, I feel giddy. I feel absolutely giddy getting a good image of this drive. So we have it preserved, the operating system is preserved, and then, well, hopefully we can get this system booted. I can use the drive emulator if I need to. It's a lot quieter, of course, although that computer has a really noisy fan on it. I'm going to end this video here. I'm going to leave it on a bit of a cliffhanger. I hope you enjoyed what I've done so far. I've been having so much fun pulling this thing apart, and the fact that we have a good disk image makes me so absolutely excited. In the next part, I need to take those power supplies out of that machine fully and open them up and look inside and kind of inspect and just make sure there's nothing inside that's going to let go, like a refa or something like that. Check the fuse, I guess reassemble the computer, and then hook up the VT100 or VT220 terminal, see if we get any life out of that thing, at least the bootstrap console, which we saw in the ROMs there, see if that does anything, and then get the drive interposer hooked back up with the hard drive or the emulator, and then see if we can figure out how to actually boot this system. My patrons have been busy at work trying to find information on this system, and so far I'm kind of reading through the comments. It doesn't look like anyone's been able to turn up any additional information besides the little brochure paper that I found. And I think there was one little mention of this computer in Computer World magazine with some software and stuff listed, but it was the tiny little blurb, that was it. So there really wasn't anything there. So if you have any thoughts or leads on documents or software for this computer or any other information really, that would be pretty cool. But maybe when this video goes live, then people will be putting their eyeballs on it and then suddenly information will turn up. That has happened plenty of times before in the past. So if you like this video, thumbs up. If you didn't, you know what to do. Definitely put a comment down below if you have any thoughts or anything about this. It's so damn cool. My patrons, their names are scrolling beside the screen over here. They make it possible I do this full time. So if you want to become a supporter of the channel, then you can do so at the link in the description below. You get early access to videos, behind the scenes things, access, stuff like that. In fact, for my patrons, they got an early rough cut of this video so they could see what this machine's all about, and that's why they're out there looking for information on the old P20 or P15. So anyhow, there we go. Hit subscribe if you haven't already, all the usual YouTube junk, and I guess that's going to be that. I'll see you for part 2 when we try to get this machine fired up and actually running. Stay healthy, stay safe. I'll see you next time. Bye.